Fine. Okay. So before, as I told you before, that there are two types of memory methods. One is the protected mode, one is the real mode memory architecture. So before we discuss about these two memory architecture, we need to know two things, right? First of all, we need to know about the segment register, because it will be needed into the next memory architecture, because we need to know how many segment register we have and what kind of information is stored into the segment register. First thing. Second thing is we need to know, or need to just revise some of the thing about the processor, especially 8086 processor. We know that all of our processors, the updated version, the current all of the processors are actually updated version of 8086. Okay, so this is the basic processor, and based on this basic processor we actually have all of them. So why we need this one? Because the real mode memory architecture is actually invented first 1978, long time ago. So at that time, as you can see, look at, there is actually several issues in this 8086 processor. First issue is this 8086 is actually a 20-bit processor. That means it has a 20-bit address bus, and we assume that if any processor is 20 bits or 32 bits or 64 bits, our address bus will be the similar type, right? So that's why this is a 20-bit microprocessor, and that's why we assume that the address bus of this 8086 is 20-bit. For that reason, our maximum memory of this 8086 processor is 2 to the power 20, right? If it is 2 to the power 20, that means 2 to the power 20 is actually 1 megabyte, more or less. Okay, so that's why the maximum memory of 8086 is 1 megabyte. Until now, there is no problem. So problem is arising when we think that about the width of the register. The problem is the address bus is actually 20-bit long, but the register width is only 16-bit long. Okay, so that is actually an issue, because whenever you are processing the data inside the processor, we actually getting 20 bits of address bus, 101010 20 bits. But whenever you try to save this address bus into the internal register, that internal register width is 16-bit. Okay, that is the problem. So what do you think, what will be the issue of this? What do you think, what will be the issue? Because our address bus is 20-bit, but register width is 16-bit. What will be the problem? First problem. I told you that our address bus is 20-bit long. That means 101010 until 20-bit, right? That is the address bus whenever you have address. But the problem is internal register of this processor is actually 16-bit. That means whenever you try to save those kind of memory location into your internal register, can you do that? No, right? You cannot do that. You cannot do that because your address is 20-bit, but your register size is 16-bit. That means you actually cannot save all the 20 bits of data into this 16-bit register. That actually is a problem. All right. Okay, so that is the issue. Actually, I need to tell you that this is the one of the basic problem. So how we can actually save or solve the problem, or what will be the solution? The solution is let me show you one thing. Let's say, for example, this is our address bus. This address bus is 20-bit long, right? This is 20-bit long. So if it is 20-bit long, that means if it is 20-bit long, right? This is 20. how many address we can have with this 20 bit of address bus. By the way, this is address bus. How much memory we can have? Of course, 2 to the power 20, right?
2 to the power 20.
Yeah, so 2 to the power 20. So maximum we can have 2 to the power 20. And if you calculate 2 to the power 20, it is more or less 1 megabyte.
1 MB.
Let's say this is 1 MB. This is our main memory. This is our main memory, and this is, let's say it's 1 MB. This is 1 MB. This is our main memory. Now the problem is our internal register. By the way, this is 8086. 80 for I mean, please consider my mouse writing, not handwriting. Mouse writing is not good. Anyway, so let's say our register size. Our register, this is our register. Our register size is actually 16-bit. Our register size is 16-bit. Okay, this is our register, this is our address bus. So the problem is, if you have a 20-bit long address, right? 101010 20-bit long address, and we can have 2 to the power 20, we can have 1 megabyte, no problem. The problem is, whenever you try to store this 20-bit address bus, address space or address of the memory into the 16-bit register, it is really not possible, right? Because you actually can store only 16-bit of this. You can save, but how about this one? You cannot save it. It will be an error, right? So the solution is for 8086 that whenever it's, instead of using 20-bit of register, now we are actually going to use 16-bit of address. Instead of using 20-bit of address, we are going to use for 8086 is 16-bit of address. 16-bit of address. Now the size of the address is 16-bit. So if the address size is 16-bit, how many we can have? Of course, 2 to the power 16, right? So 2 to the power 16 is more or less 64 kilobyte. 64 kilobyte. That means at the same time, we actually can have this kind of 64 kilobyte of memory at the same time. That means at a time we can use 64 kilobyte of memory at the same time, because our processor cannot 64 kilo, because our processor cannot do much more than that. Okay, so you might thinking that whenever we are using 16 bit of the address bus, how about the rest of the 4 bits? Actually, what actually they do, second option is we use 16-bit of address 10101010, and we can have 64-bit of data, 64-bit of address at the same time, and you actually, this 64-bit of data actually called segment. So we have segment, and you can use all of them, all of the segment, like the same way. That means that's how we divided our memory into 64 kilobyte of segment, and we can use our full memory. As we know that previously into the segment register, that our processor cannot use all of the memory at the same time, right? For this case, the memory actually divided into small segment, and each of the segment is actually 64 kilo. Okay, because we are going to use 16-bit address. All right, because it is 2 to the power 16 is 64. Fine. So the problem is, whenever you have 16-bit of address, then whenever you're using the system bus, right, this is one of the part of the system bus, right? So whenever the processor wants to communicate with the memory, what will happen? You have 16-bit of address, but the address space is 20-bit. How about the rest of the 4 bits? The solution is we are putting 40 here. 0 0 0 40 here. That means we have 16 bits of the address, and the rest of the 4 bit will be covered by 4 zeros. Okay, that's how we can have different segment, so many segment based on how much memory you have. In this case, we have 1 megabyte of memory. We have each segment is actually 64 kilobyte long, and although our address bus is 20 bit, so the rest of the bit will be filled up by 40. Let me show you one thing. Let me finish this one, then you can actually ask. Let me show you one thing. I think you can understand if you can see this one. So this is the example. This is the example. By the way, before that, one more thing you actually need to know, that in the real mode, because we have so many segments, right? We have so many segments, segment 1, 2, 3, 4, 5, 6, so many. So how the processor will actually know that which segment and which part of that segment is actually your data is located? So whenever you try to locate the data, how do you know that which segment and where is that segment? So to identify the segment and to identify your specific data from the memory, there is one notation or one format by which you can create or you can write your memory. That notation is two things you need to know. One is segment, another one is the offset. Let me give you one example. I hope you will understand what is segment and what is offset. For example, you have a very large library, for example, our IBG library, and you want to find out a book which is called assembly language. Okay, how do you find this book into that big library? You have an option that you actually go from one, because there is no level. Let's say there is no level on the shelf. So how are you going to find it? You have to find each and every shelf and each and every rack, right? Then you actually can find the assembly language book. But if you know two information, right, regarding the book, just two information, you can easily find the book. First information, if you know the the rack number, right? There are, let's say there are 50 rack, and we know that in fifth rack we have this book. So first information is the rack number. Let's say shelf number, not rack, shelf number, shelf, bookshelf. So we have fifth bookshelf, right? So the shelf number is 5. So you go directly to book number, shelf number 5. But that shelf number 5 is actually 10 rack. So which rack you can find the book? You don't know. So if I tell you also the rack number also, let's say it is third number of rack, then you can easily find the book. The name is called assembly language. That means you go to the shelf number 5, and then in that shelf number 5 you actually counted, okay, there is a third shelf, so you can count 1, 2, 3. So this is the third rack. So I just looking at my book assembly language. So these two information will be very helpful to find the specific book among the 1 million book, no problem. Same as here in operating system, same as here in this real mode. To find your specific data in a specific segment, you actually need two information. One is the segment address. That means you know that each segment is actually has a unique address. Okay, one is the segment address, another one is the offset. Okay, segment is the very similar to the bookshelf number, right? Bookshelf number, let's say 5, and offset is the same as the rack number, third rack, 0 to, I mean, it should count from 1, 2, 3. Okay, third number of rack. So this is the same way we actually can find our very specific memory location into the from the memory by using this technique. Okay, all right. So there is an example. Let's say there is an example. You can see that this is the way we can write the memory location. By the way, H means hexadecimal, and whatever number you're seeing is actually the hexadecimal number. So 1100 is the base address of the segment, and 450, again, it's a hexadecimal number, is actually the offset. Look at the picture. This is the picture, actually I get it from the same thing. So we need to know two information. One is segment address, another one is the offset on. Then we actually can find out, yes, this is our desired location to get the data. Okay, so this is the full this is one of the maybe one of the cell of the memory. There is another cell, there is another cell, maybe there is another segment, but here what you need to know is actually starting from here. They say that is the base of the segment. You start the base of the segment, and the offset is you have to add. That means it's actually range from where the data will start and where the data will end. That is the range. That is called offset. Okay. By the way, another information is, if you combine this segment and offset, this combined information is actually, you can call it logical address of the memory. This is actually the logical address. I hope you know what is logical. That means this is a address by the software. This is a virtual address. Okay, not a real memory address. Okay, this is actually a logical address. But in real mode, we can easily convert our logical address, which is used by the programmer. Generally, as you can see, it says the programmer have to be concerned with the logical address only, because programmer like us, like you, no need to know about the physical address. By the way, physical address of the memory means the hardware address of the memory. Okay, it's hardware address of the memory, and programmer needs to know only the logical address, nothing else. So how we can find the logical address? We can find the combination of segment and offset value. If you know these two information, that will create, or that will have your logical memory address. Okay, and there's some other way we can actually have the best thing of this real mode architecture is, every logical address of this type of memory architecture has its corresponding physical address. That means if you have a logical address, you can easily find what is the corresponding physical address. Physical address means original hardware address. Look, you actually can find it easily, because the left side is the logical address, right side is the physical address of the memory. Okay, and that is one of the basic reason, and one of the reason that it is called actually real mode memory architecture, because there are some real memory location. That means the original physical memory location here. Okay, that is one of the reason it's called real mode memory architecture. Fine, whatever we have just said, do you remember about this one, that we have a 16-bit memory, but our address bus is 20-bit? So what you are going to do with this extra 4-bit? Okay, the answer is actually here. Look the segment base. Look how many digits we have here. 4, right? And I told you that these are hexadecimal number, and I think you remember that each hexadecimal number can be represented by 4 binary digits, right? That's why if you convert this one into binary number, it can be actually 16-bit of binary number, and that is our 16-bit here. Okay, that is the 16-bit. Okay, that is our logical address. But we said that how we can find that from 16 to 20, we will add 4 0. That is a very important information is written here. Least significant 4 bits of 0. It's assumed that least significant bit. By the way, I hope you know what is least significant. Least significant means, by the way, we have 1100. Which one is the least significant bit? Here, 1100. Least significant bit, it's actually 0. Here is actually always the rightmost one, right side. All right, so this is actually least significant. And okay, all right, that is, and this one is actually most significant. So we are not talking about most significant, we are talking about the least significant. That means according to the rule, it says that it should be added 0 into the least significant digits, right? Look what they have done. We have a value of 1100. By the way, these are all hexadecimal number. And look at the value here, physical address. But that means how we are going to convert from 16 to 20. So in this case, what is the difference? They actually add 1 extra 0 here, right? Because of this, that we need to add 1 more 0 into the least significant bit. By the way, 10 in hexadecimal number means 40 into the binary number. Now how many bits we have here? 5. If each of the bits got 4 bits of the binary number, altogether we have 20 bits, right? So that's how we can fill from the 16-bit address into the 20-bit address bus by filling up 0000 into the least significant bit, not most significant bit here. So the first 16 most significant bit will be our address, and the last, I mean not last, I mean the other 4 least significant bits will be 000 and 0. And that's how we actually can convert from logical to physical, and also from 16-bit register into the 20-bit register. And this is important. You might thinking why we need to do all of this, because whenever it was invented in 1978, our register size is 16, but our address bus is 20. Okay, because all other buses are almost the similar size. We they're actually having some problems, so they solve this problem in that way that the large memory can be divided into small segment like this, okay, based on the size of the register, and then they can use the full memory. And this one is so popular that all consequence, I mean all other updated version of the Intel processor actually follow this kind of method. All right, that is the real mode memory architecture. Fine. Okay, you can ask me question now.
Sir, converting into physical address, sir. Like you said, one number, like 10 means 40. That means 4 number is equals to 5 into 4 equal to 20 bits, sir. I didn't get that. Like, how did we convert this 20 bit to 60 bit in physical address?
I told you that whatever number you are seeing here, right? These are all hexadecimal number, right? All hexadecimal number. 1100. That doesn't mean that they are binary number. They are hexadecimal number. So if you convert this hexadecimal number into binary number, you actually have how many bits? 16 bits, right?
Yes, sir.
16 bit. But our original address bus is 20 bit, right? So
Yes, sir.
what is the rule? The rule is we assume that the least significant 4 bits are all 0. That means least significant bit, where is the least significant bit here for 1100? This side, right?
0.
No.
Yes, sir.
That's why they have added 1 extra 0. Look, if you compare these two numbers, this 0 is actually extra, right?
Yes, sir.
This is actually that extra 0 we are talking about to make them the 20-bit address.
Yes, sir. Get it now, sir. Yes.
All right.
But immediately the conversation we convert hexadecimal to binary, we put the extra 0 to the left side, not the right side.
No, the right side.
Yes,
here.
sir.
This is the extra 0. This is the extra
But
0.
in the conversation, we used basically we used in the left side.
I mean, sir, I think it wants to mean, sir, when we convert decimal to binary, we put the numbers in the, we put the zeros in the left side. But in here, you are saying that we are putting 0 in the right side. But if we put 0 in the right side, it will make it.
No. Listen, you are not understand properly. The rule is whatever address we have here, the rule is to make it from 16-bit to 20-bit. How we are going to from 16-bit to 20-bit? We need to add 40 into the least significant bit. All right? That is the rule. That is the rule. So this, according to the rule, that's why we have added 1 extra 0 here, so that we can have 20-bit long address for our address bus. That is actually the basic thing. Okay, why you are saying that there are 40? Why they actually say that 40? Because each 0 for hexadecimal number is actually equivalent to 40, right? Because each digits of hexadecimal number have 4 equivalent binary number. All right, that's why we are talking, that's why we are saying that least significant 4 bits of all are 0. Do you get it?
Something like if we want to make it 8 bit, then we will only write 1 1.
And what?
So like here is